Hello guys, so chapter 2, part 2. So we saw, right, numbers of protons is equal to atomic number, right? And the number of protons plus number of neutrons is equal mass number. Therefore, to calculate numbers of neutrons, we're going to do a subtraction. Mass number minus atomic number, right? For example, here, practice problem 3. An atom of lead has a mass number of 207, right? How many protons are in the nucleus? How many neutrons and how many electrons, right? Okay, let's get the lead, right? Pb is right here. 207 is the mass number, right? So, okay. 207 mass number, and the atomic number is 82. Okay. So lead 207 and 82. So here's a 207 here. I'm sorry, it was not well written here. So how many protons are in the nucleus? The protons is the atomic number, right? So 82. How many neutrons are in the nucleus? So to calculate neutrons, we're going to do a subtraction, right? Between mass number minus atomic number. And we're going to do a subtraction here, right? We're going to have 207 minus 82. So we're going to be 125 neutrons. Okay, so 125 neutrons. And how many electrons? So we have to hit this atom, right? Lead. There is no charge here. That means a neutral atom. So if there is no charge, protons equal to neutron, to electrons, right? So that means here 82 electrons, 82 protons, and 125 neutrons. Okay, so next topic here, isotopes. Isotopes are atoms of the same element with different masses. So isotopes have the same number of protons, but different numbers of neutrons. Right. So isotope symbol represents the particular isotope of an element. So you have the oxygen, 16, that has 8 protons, 8 neutrons, and 8 electrons, right? If you subtract here, 16 minus 18, 8 neutrons. The phosphorus, atomic number 15, so 15 proton and 15 electrons. Do a subtraction, 31 minus 15, and you have the 16 neutrons. And the zinc here, atomic number 30, mass number 65. So protons 30, electrons 30, and neutrons will be a subtraction here. 65 minus 30 here. Right? Okay. Okay. So the isotopes, they have the same number of protons, but different numbers of electrons. And the isotope symbol represents the particular element, right? So will be a mass number on the top, upper left and atomic number lower left corner here. Now here, average atomic mass, Because in the real world, we use large amounts of atoms and molecules. We use average masses in calculations. For example, the periodic table, the number that is periodic table here, the atomic mass is the average for each element. To calculate this atomic average, we're going to take the sum of the isotope mass plus the fractionary natural abundance for all isotopes. The masses of any atom are compared like carbon 12, being carbon 12 has 6 protons and 6 neutrons, being exactly 12. Right. So atomic mass is not the same as mass number. So, okay, here, isotopes of chlorine and average atomic mass. We have like an example. This equipment here is the equipment that you measure the isotopic abundance. So you already introduce the sample here and pass all the steps by heating the magnet here and then the detector, and this is what show the in the computer screen here. So what it says, like for example here, chlorine, isotopes of chlorine were introduced here, and it shows that we have about 75% of chlorine 35 and 24.24 percent of chlorine 37. So what's the average here? So what we're gonna do is like this. So what we're gonna do, let's use the problem 7. Demonstrate how the average atomic mass listed on the periodic table for chlorine is obtained from its two naturally isotopes. Chlorine 35 has a mass of 34.969 atomic mass unit in the natural abundance of 75.75%. And then chlorine 37 has a mass 39.966 in the natural abundance of 24.24%. So what's going to be the how to answer here? We're going to take the mass 34.969 times its abundance here, 75.75 percent here, divided by 100 as percent. Then this here is for this first isotopes, right? Take the mass, atomic mass units, and the percentage. Multiply them. Plus, let's go the second isotope. The second isotope here, the atomic mass is 36.966 times its abundance here, 24.24%. So then I'm going to calculate it here, right? I'm going to open parentheses here. 34.969 times, remember, I'm going to divide this by 100. They're going to be 0.7575 close parentheses, plus, open parentheses, then the second one. 36.966 times, we're gonna type here this one already divided by 100, that would be 0.2424. The answer is 35.449, right? But here in the question, we have the least one has 4 significant figures, so our answer will have 4 significant figures. So the answer is gonna be 35.45. Atomic mass unit. Oh, yeah, the average here. Atomic mass unit here. That's gonna be exactly what is shown here. So the numbers in the periodic table here, they show like they're around the average for each isotope. Now, periodic table. So let's just go for improvement resolution. Okay, the periodic table. In 1869, Mendeleev created the periodic table. He organized the elements, increase atomic number, atomic mass, and arranged the elements into groups with similar properties. So here, the guys in the group 2A, they have similar properties. The guys in the group like 7A, they have similar properties. The elements, right? So the periodic table is a systematic organization of the elements. In the current periodic table, elements are arranged in order of atomic numbers. So hydrogen, the first one, number 1, helium 2, lithium, beryllium, and go on here. So you have different colors, right? You have metals, non-metals, and metalloids. So the metals, the blue, all the blue here, they are metals. The only like hydrogen is the only non-metal that is on the left, because there's one that has just one valence electron, and everyone here in group 1 has one valence electron. In group 2, all they have 2 valence electron, right? So hydrogen is a non-metal, and actually hydrogen is the only that does really belong to any group. It's here just because has one valence electron as the other ones. The other ones. Okay. Metals, blue, no metals, the yellow and the green, the metalloids. So metals. The metals, they are the left side of periodic table. They have some metal properties like shining, conducting heat and electricity. Like they are solid with exception mercury. Mercury is the only metal that is liquid. It's not solid. In the metal, they have high melting points. No metals. All the no metals here, hydrogen and these elements here, yellow. The no metals, they are on left periodic table with including like hydrogen. They can be solid like carbon, can be liquid like bromine, or gas like neon. You have the gases, right? Noble here, the noble gases here. The non-metals, they are poor conductors of heat and electricity. They have low melting points and densities. The metalloids, the elements here in the green, just a few, right? They are on the step-like line are metalloids here. The one increase. They are better contours of heat and electricity than nonmetals, but still not as good as metals. And the metalloids, they are semiconductors. So they got the elements here in the semigroup, they are the lines here. The vertical you count the groups family. In horizontal, we count it as periods. Like first period, this first line here. Second period, the second line. Okay, chemical formula, right? So chemical formula indicates the elements present in the compound in the relative number of atoms of each one. So like water, hydrogen, 2 hydrogen, 1 oxygen, H2O. Sodium chloride, NaCl, 1 sodium, 1 chlorine. Magnesium nitrate, 1 magnesium, and 2 nitrates. This is why nitrate is a polyatomic ion. So when you have more than one polyatomic ion in the chemical formula, we are going to add a parenthesis. That means this compound, magnesium nitrate, has 2 NO3. So, okay, let's count how many magnesium have here? Only 1. Yeah. How many nitrogens? Nitrogen here is inside the parenthesis, right? Between parentheses, and it had number 2 here means 2 nitrogens. In the oxygen, you have 3 in each nitrate. And you have 2 nitrates, so 2 times 3, 6 oxygens. The number in the bottom here, the subscript to the right of the symbol of an element tells the number of atoms of that element in one molecule of the compound. Okay, talking about chemical formulas, we have 2 kinds of chemical formulas: empirical formulas and molecular formulas. The empirical formulas give you the lowest whole number ratio of atoms of each element in the compound. In molecular formulas give the exact number of atoms of each element in a compound. For example, here, the molecular formula was C2H2O2. So what is the lowest number here? The ratio divide everything by 2 is say HO. The empirical formula that's the lowest whole number ratio will be CHO, because if you divide everything by 2, CHO. And then H2O, water. What's the lowest number here? The lowest subscript here is 1. That means you cannot divide by anything, right? That means for water, H2O, the lowest, the empirical formula is equal to molecular formula. If you had like 8202 for 8202, the lowest number here is a 2, so that means this is the molecular formula, for example, for hydrogen peroxide, H2O2. This is the molecular formula, and the empirical formula will be HO. Empirical formula, right? Right, and the picture molecules, you have a molecular formula, just like the symbols as it is here. Structural formula that shows the bond in a 2D plane here. This perspective drawing here is also shows the bond, right? But shows also like try to do like a 3D idea right here. The dashed wedge is a bond behind the page, and this wedge is a bond outside the page. So this one is a like 2D idea, and this like 3D. Then you have this model here, ball and sticky model, represent the atoms, the balls represent the atoms, and the lines, the bonds. And then the last one here, space filling model. The atoms fill the space between each other to more closely represent our best idea for how the molecule might appear. If we could scale into visible size, it would be more likely this one. Okay, so have we already answered this problem 11, right? So C6H12O6 is the molecular formula for glucose. The lowest number here is a 6. So let's divide everything by 6. You'll be 6 divided by 6. 1, 12, 2, and O will be 1. So empirical formula, CHO, in molecular formula C6H12O6. For N2O, the lowest number is already 1 here, right? So the empirical formula of nitrous oxide is the same as its molecular formula. By the way, nitrous oxide is used as anesthetic and commonly called laughing gas. Okay. Then types of compounds. You have ionic compounds. They have a metal and non-metals bonded. Ionic compounds are usually formed when ionic bonds occurs with oppositely charged ions. So one is gonna be positive and another will be negative. In a chemical reaction, atoms can lose or gain electrons to form charged particles called ions. There are two different kinds of ions, the cations and anions. So ions is when you have a charge, right? Cations, they have a positive charge because you're going to be losing electrons. And anions, they have a negative charge because you'll be gaining electrons. So the metals, they lose electrons, will be cation because we lose electrons, so we're going to be positive, and the non-metals will be the anions because we'll be gaining electrons, so the charge will be negative. Right? So for example, here, sodium chloride. Sodium is a metal, and the chlorine is a non-metal. So the sodium atom will loses an electron, and chlorine gains this electron. So sodium gonna be the positive, and chlorine will be the negative. So binary ionic compounds. Electrons are transferred from the metal to the non-metal, right? From the metal to the non-metal. And oppositely charged ions attract each other. And only empirical formulas are written, right? And the positive ions is the cations, right? And we're gonna be the metals, like group 1A, 2A, 3A, the groups. The positive ions, so they lose one or more of the valence electrons to form ions with a positive charge. So they lose electrons until they have the same number of the valence electron as the nearest noble gas, usually 8 valence electrons. So Sodium here has a total 11, right? 11, atomic number is 11, so 11 protons, 11 electrons, right? So they're gonna be, if they lose one electron, right, it will be 10 electrons. And so here, sodium has 11, right? Sodium has 11 electrons. After loses one, will be like neon. Neon is an other gas, and it has 10 electrons. So it says, so the ions, the atoms, they lose electron, the metals, until they have the same number of valence electron as the nearest noble gas. Like sodium lost one, will be like neon. Neon has 10 electrons. Right. In a chemical formula, for an ionic compound, the symbols and subscript are written in the lowest whole number ratio of the atoms or ions. So, of ionic compounds, the sum of ion charges equals 0. So, the total positive charge is equal to the total negative charge, like here. Sodium plus 1, chlorine minus 1, 1 minus 1, 0. Right? Okay, so reading chemical names from chemical formulas when name an ionic compound. So when name a compound, the name of the metal is written first. So here you have K2O, so have potassium. Potassium is a metal, right? So let's write potassium first. And it's the same name as the name of the element. So potassium is still potassium. And then the name of the non-metal is the first syllable of the metal plus the metal name, non-metal name plus I, like here. Oxygen, we change oxygen to the end to I, so it will be potassium oxide. And it is, right, so potassium oxide, metal, non-metal. And here, calcium, right, oxide. And about the letter C. Magnesium, right? We not change the first one, it's still called magnesium. And about this one will be bromine, right? But we're gonna change it to ide, so we're gonna be magnesium bromide, right? Okay. Right now, write the chemical formulas from chemical names. You have here the compounds, the names, and the formulas. The formula for ionic compound is written from its first part of the name that describes the metal ion, and the second part of the name that specifies the non-metal ion. And then subscripts are added to balance the charge. So first one, write the symbol. So like here, right? Iron to chloride. Okay, so how that thing? So write the symbol like iron, write iron first. Then the symbol for the non-metal. So iron, Fe, chlorine, Cl. Okay, right? They make the magnitude of the charge of each ion without the subscript here. So it says iron 2 chloride. So it's already saying that iron is started 2 plus. So Then the transition metals, we write the Roman numerals as the charge. So iron is a transition metal, iron 2. So that means the charge for iron is 2. So chlorine is a halogen. So the chlorine, all the halogen is here, the group 7A, the verb charge 1 minus. So if chlorine is -1 and Cl is a -2, how many chlorines do you need to make total 0? So remember, the net charge needs to be 0, right? So you need 2 minus, so 2 times -1, 2 cancel out with the iron 2 plus. So 2 from the iron, -2 from the chlorine, because 2 minus 1 is -2, is equal to 0. The net charge is 0. So like here, the magnesium, what here? What's the name for this one? Magnesium nitride, right? So magnesium, let's say now I was given the name, magnesium nitride. Magnesium is at 2 plus because the group 2A. And nitrogen is a 3 minus. So let's say that we don't know the charge here. Let's say that the problem gave you just the charge. Magnesium 2 plus, nitrogen 3 minus. How gonna be the chemical formula here? So the charge of the metal will indicate the subscripts of the non-metal. We've seen here that 2 plus for magnesium will be the subscript for nitrogen. And then the charge for the non-metal will be the subscript for the metal here. All steps here. Write the symbol of the metal and its charge. Write the symbol of the non-metal and its charge. Make the magnitude of the charge of each ion without the sign. So make the subscript of the charge of each ion the subscript for the other ion. And if possible, reduce the subscript to the smallest whole number ratios. And the last one, make sure the sum of charge of cations is equal to the sum of the charge of the ions. Right? So I'm gonna pause here, stop here to make another video later.